All right, before 4 o'clock rolls around, let's do a really quick audio check. Can you hear me okay? Awesome. Thanks for the feedback. Sweet, sweet. How's everybody doing this afternoon? Wow, okay, cool. We've got 14 people watching, so I think that's a pretty good number to get started with. One thing I'm noticing is that the latency between what I'm saying and what I'm seeing in the chat is pretty extreme, probably around 25 seconds. Um, so if it looks like I'm not seeing your comments immediately, that's what's going on. Um, but yeah, let's just go ahead and get started. So my name is Warren Moore. I don't know how you came to be watching this today, but maybe you follow me on Twitter. Maybe you've seen, my book on metal, some talks or whatever. But however you got here, welcome. Today we're going to be talking through a pretty fun little exercise in metal, actually a whole bunch of small exercises that are designed to kind of be an introduction to shader programming. And a particular kind of shader programming to mostly just fragment shaders. That'll kind of be the way we uh, get introduced to this stuff. It's going to be kind of mathy. But the intent here is not to talk about the Metal API very much at all. I'll walk through the template so that you're kind of oriented to what's going on. But again, this is not really so much a Metal talk, lecture, whatever, um, as much as it is just kind of working through the shading language. Florian asks, why not do the same with compute? Um, Probably the only reason is because compute is not as visual. I mean, certainly you can do image processing, but my emphasis here is not necessarily so much on even practical applications or what one can do with GPU in Metal, but rather just something that's closer, I think, to like Shader Toy. And I think the popularity of Shader Toy sort of, indicates that people find visual shaders, fragment shaders, and so on to be an appealing way to learn and get their feet wet. So what you're seeing on the screen right now is a tweet from Leon Denise. I apologize if I'm mispronouncing that, but he's actually the instructor that created this exam, and I like it because there's a lot of interesting effects that can be showcased here, and it's not too complex to get started. You can see that we have this image of Pikachu, and we're going to manipulate and distort it in various ways. And yeah, so let's just hop over to the template. If you can't read the code, then please say something in chat, and I will try to make it a little bit bigger. I think it should be about right. But if you're viewing on like a mobile device, it's probably going to be a non-starter. So I apologize for that. In any event, we'll just start out in the view controller. Well, first of all, to give you an idea of what this looks like when it runs, it's pretty much just a window with a picture of Pikachu, as expected. So the way we actually do that is I'm using MetalKit here. So I've got an MTK view, and I just add that as a sub view of the root content NS view of the window that I created in my zip file. I do a little bit of wiring up to let the metal view know which metal device to use, and I also create an instance of this renderer class that's going to do all the heavy lifting. So we'll dive into the renderer class next. Now, And basically what that consists of is sort of a renderer delegate that loads a model, loads the texture, creates the various pipeline states. None of this is material to what we're actually doing as far as the shaders are concerned. I just want you to see maybe like how much code is required to stand this thing up. It's not much. It's a couple hundred lines. And so then we actually create those pipelines, generate a couple of textures that we're going to be rendering into off screen, and then later on when we actually draw, we basically draw the Pikachu mesh into an off screen texture, including using a depth map to get correct depth sorting, and then draw a full screen quad that basically maps that image onto the viewport of the window. And the reason for that kind of two-step process is that we're basically going to be working mostly in texture coordinates. So those are it's kind of a normalized space, which I'll describe it more in a second. But the idea is that we're going to be manipulating those texture coordinates themselves rather than, for example, manipulating the vertex coordinates or what we were actually writing from that initial off-screen pass. I'll go ahead and actually do a GPU frame capture of this app so that you can kind of get an idea of what I'm talking about when I say off-screen pass versus just the full screen quad render. Michael asks, we're not drawing Pikachu as an SDF. Not today. Actually, all the stuff that we're going to be doing today is strictly fragment shaders. And maybe in a couple of weeks, we'll get around to the actual drawing Kirby as an SDF. Full disclosure, we're not doing any ray marching or SDF stuff today. So if that's what you're here for, I apologize. We will get around to it because it's one of the cooler parts of the exam, but I can't do everything at once. So what you're seeing right now is a GPU frame capture of the second pass, that second render command encoder. And what that one does is it just essentially blits more or less from the texture from the preceding pass. And I'll go ahead and try to step over into that. The tool, I was going to say the tools are a little bit glitchy, but they're working perfectly right now. So you can see that the mesh itself is comprised of, on the order of probably a couple thousand triangles or so, maybe a few hundred. And I can turn off wireframe for a second so you can see you got the color buffer on the left and then the depth buffer on the right. Not too fancy, just really drawing one mesh. So then what that produces, of course, is this color texture, which again we go on to map onto the full screen quad that sort of fills up the viewport. So I'll go ahead and release that GPU frame, and with no further ado, I'd like to actually just go ahead and jump into the shaders themselves. I agree. Swift actually is even better than Objective-C in terms of bringing up like sample code and projects. It's pretty terse, and I like working with it these days. I've been a Swift hater in the past, but for certain things, for many things actually, it's pretty great. So here I am inside the post-processing vertex and fragment functions, and what we do. I'm not going to go through the shaders that actually draw Pikachu, or I will if anybody's really curious, but it's immaterial to what we're trying to actually achieve. So what we want to do here is basically take in one of these quad vertex in structures, and that just consists of a two-dimensional position and a two-dimensional set of texture coordinates. And those positions are actually already in normalized device coordinates. They're already in clip space. So we don't actually need to manipulate them in any way. We just kind of pass them through. And those range from -1 to 1 in both X and Y. And that's a system in which X is to the right and Y is up. And then the texture coordinates actually range from 0 to 1 in X and Y. But that's a coordinate system where Y points down. So it's important to realize that there's kind of a flip that happens when moving one to the other, as well as a scale and bias. So just remember, keep that in mind, that oftentimes when we're manipulating texture coordinates, some of these transformations are going to kind of feel backwards because we're actually kind of manipulating texture space rather than manipulating texture coordinates. That should become apparent as we kind of roll through here. So first things first, inside the fragment function right now, I'm creating a local sampler that just is going to sample using those normalized 0 to 1 coordinates, and also uses a linear filter to kind of smooth things out a bit. And then I'm just, in the interest of staying terse, I'm basically writing UV as the pair of texture coordinates. And so I extract those from the rasterized fragment value and get those interpolated texture coordinates again in that normalized space. And then I sample the Pikachu texture, the off-screen rendered texture at those coordinates, crunch that down into a half precision vector, and then return it. And so that becomes of course, value of the corresponding pixel. All right, so let's take a look at the exam and what it wants us to do first. So if we look at it, the very first one after the image itself is the mirror, and this is a vertical flip in essence. So how do we go about that? Basically, what we're doing pretty clearly is manipulating the y coordinate of the textures, or the texture coordinates. So that's as simple as just saying that the uv dot y is equal to 1 minus uv dot y. And so what that does is, in essence, it sort of flips the y-axis. So if I run, you can see that we turn upside down. So I would consider that a success, right? Looks pretty much. And these are not going to be pixel perfect, by the way. Sometimes the constants that I choose on the fly are not actually going to correspond precisely with what you see on the exam. But that's hopefully okay, because our intent is to sort of capture the spirit rather than the exact pixel perfect result. So just moving right along, Michael, yeah, this is the syntax here is metal shading language as opposed to GLSL. So you don't actually assign to a frag color variable. Instead, what you do is you actually return the value of the pixel from the fragment shader. That's one pretty profound difference between GLSL and metal. All right, so moving on, we want to achieve this symmetry effect. And so that, in essence, kind of folds the image around the x-axis or around a horizontal line. So one way to achieve this is basically by checking if the y-coordinate is greater than a particular threshold, like let's say 0.4, and then if so, offsetting it by some quantity and flipping it upside down. So the way I like to think about this is, if I'm going from top to bottom, my y-coordinate is basically going to run from 0 to 0.4 and then 0.4 back to 0. And if I'm thinking about that conceptually, what I'm thinking about is kind of a V shape, right? And what looks like a V shape? Probably absolute value, right? So one thing that I like to do when I'm doing this kind of stuff is actually, let's get rid of that, is literally just build a function in Grapher that represents what I'm trying to achieve. So I'm just going to open up Grapher and say, okay, well, if this is the default mapping, right? If coordinates run from 0 to 1, then we have an identity mapping by default, right? But what I want to do instead is actually kind of bounce around the that particular threshold. So I'll start out by just using absolute value of x here to kind of show like that's getting to what I want, right? Like that's, there's definitely a bounce there, but it's not in the right place. So I want to shift it right by subtracting a half from x and then actually flip it upside down and then finally bias it by another half. And what that does is it actually achieves that intended effect of going from 0 to a half or whatever the threshold is and then back down to 0. So I can actually take that expression and bring it back into Xcode. And so whereas that one was for mirroring, what we want to do instead is basically say UVY is that expression. Actually, it didn't copy correctly, so I'm just going to type it in again. Is the absolute value of uv.y minus 0.5. right? So I think that's right. We'll find out in a second. Right, so we can see that we're actually getting the intended mirroring effect. And again, that threshold is not identical, but the effect is the same, right? So if we go back to the exam, pretty close. That is our symmetry effect. Cool. Did I miss any questions? Florian asks, is there a public C++ API, I assume for Metal these days? No. If you want to interact with Metal from C++, you pretty much have to use Objective-C++. Or if you want to get really clever, you can try wrapping it, but you're still going to be ultimately talking to an Objective-C++ API at some level of that stack. Okay, so moving right along, the rotation one actually has a lot of interesting tricks to it, which will actually just sort of build up as we work through it. But in essence, of course, the idea is that we want to rotate around the center of the screen. So a naive implementation of that might basically say, well, what is the angle of a given pixel, and then sort of just offset that angle by some quantity, and then recreate the coordinates in that sort of rotated frame. So we'll start out by trying to do that. And one quick way of getting the angle between the x-axis and a pair of coordinates is by using the atan2 function. So if you're not familiar already with arctangent, I'm not actually going to go through the trigonometry that sort of makes this work, but in essence, the atan2 function takes a pair of coordinates and expresses its angle relative to the x-axis. So what I can do here is actually just pass in uv.y and uv.x. By convention, atan2's parameters take the y coordinate first and then the x coordinate. It's mostly an historical accident as to why that's the case. And then, so that gives me the angle, but I still don't know how far I am from the origin. So what I can do now is basically also take the length of those coordinates. Again, this is the length in texture space of the texture coordinates themselves. And that means that if I know how far I am from the origin and I know the angle that I'm at, I'm basically in polar coordinates at this point. And I can reconstruct the initial value by actually just building a vector that consists of the cosine of that angle and the sine of that angle. And then if I multiply through by the length again, what I would expect is that I actually get back to precisely where I started. So let's go ahead and see what happens when we do that. Good. So far, so good. We're actually right back where we started, and we're just doing a lot more math to get there. But there's a good reason for that. So naively, what I might want to do is just say, okay, well, now that I have that angle, I want to offset it by some quantity. Let's see what happens. Right, okay. So we rotated kinda, sorta, but we didn't actually rotate around the center of the screen. Instead, we kind of rotated around the corner. And also, we might be looking a little bit pudgy, almost like we got stretched out or distorted. We need to address both of those issues. The first thing that I want to do is whenever I rotate, right, I'm rotating around the origin of the local coordinate system, which in this case is in the corner of the screen the corner of the window, as opposed to in the middle. So a way to ameliorate that is actually just to initially offset the coordinates by 0.5, which will move kind of move us to the center of the screen or move the coordinates. There's kind of an inverse relationship between the two, right? But the point is that we're trying to put the center of the figure on the origin of the local coordinate system. So once we've reconstructed those coordinates, we'll actually go ahead and offset back to the middle. And now we should actually... Sure, definitely. Sorry about that. Caroline asked to put Pikachu off to the side so that he's not obscuring the code. That's a good suggestion. I'll try to keep it off to the side. Now, I know I'm moving kind of quick through here, so I'll try to post all this code on GitHub, and also the live stream will be posted later on YouTube. So I apologize if I'm moving too quickly. I'm always more than happy to slow down and answer any questions. Okay, so what have we achieved here? We've basically moved ourselves back to to a more suitable origin to conduct this rotation in, and then once we do the rotation, we kind of pivot back, or rather translate back, so that our figure is back in the middle of the screen. But we have one problem here, and that is that as this angle increases, I'll go ahead and do it in a couple of different steps. As this angle increases, the distortion actually gets substantially worse, to the point that if we actually rotate by pi over 2, 90-degree rotation, counterclockwise, then we wind up being extremely distorted, right? We're stretched out along that axis, Pikachu's horizontal axis, what has now become our vertical axis. So how do we fix this? Well, the problem arises here because the aspect ratio of the coordinate system of the window is not the same as the aspect ratio of the texture coordinates. Because the texture coordinates are in this space that always runs from 0 to 1 in each axis, regardless of aspect ratio, we need to correct for that. So one way that you can do that is actually just by literally computing the aspect ratio of the viewport. And if you were just rendering directly into a drawable, you may not have ready access to the texture that you're drawing into, because you can't simultaneously bind a color texture as a parameter of your fragment shader and also write out to it as a color target. So instead what you can do is pass the dimensions of the image in as a uniforms using something like set fragment bytes, which I haven't done here because excuse me, I do have full access to the texture that I'm sampling from, which has the exact same dimensions and aspect ratio of the viewport, right? So what I want to do here is basically use these utility functions on texture, get width and get height, to form the ratio between the two. And in this instance, the ratio is going to be like about 1.2. It's kind of it's a little bit stubbier than like a 4/3 monitor turned on its side. And then now that I have the aspect ratio, what I want to do is manipulate the x coordinate by that aspect ratio. I'll say uv.x is multiplied by the aspect ratio. And then once I've gone through that process of reconstituting, I want to reverse that. So in essence, what I'm doing is I'm moving into a space where the texture coordinates that I'm manipulating, even though they're sort of in this intermediate space, essentially are aspect corrected, so that when we actually do stretch that texture space back out to cover the viewport, we get that stretching basically gets undone. And so you can see that now we can, when we rotate, we actually rotate in an aspect correct fashion. And we can try one of these more intermediate values as well to show that still works, even if the angle is a little bit lower. Great, awesome. I know that was a little bit more involved than some of the preceding ones, but this concept of sort of manipulating via the aspect ratio is pretty important. So it's something that we'll see again in a moment. So I think it's important to talk about it. Okay, so this next one is a little bit of a softball. It's just zoom, and it seems to me like all we want to do is just kind of multiply the texture coordinates by some scale factor in order to create that effect. So let's see what happens if we try to do that a little bit naively, and then we'll walk through like why it doesn't work exactly as we expect. So I'm going to go ahead and keep this code that kind of shifts us over. In this particular instance, the aspect ratio is not going to matter, so I'm just going to eliminate some of that code just to sort of boil things back down. So in essence, what I'm doing here is just doing that sort of shift back to the origin, and then shift to the middle of the screen. And initially, I'm actually going to strike even that and see what happens if we just say something like UV is multiplied by 4, right? And what I'm intending here, right, is I'm actually going to use 2, is for that to have the effect of zooming in. Now let's see what actually happens. Actually, what we can see happens is we zoom out in effect, and we also zoom toward the corner of the screen, which is not really what we want. So what I can do instead is say, however much I want to scale up by, I'm going to multiply by the inverse of that. So if I multiply instead by a half, then we get something more analogous to zooming in by a factor of 2. Now, of course, this is still not what I want because the zooming is basically occurring from the corner of the screen as opposed to around the center. So I can add that fix in to offset out into toward the origin and then back, and you can see that now we're zooming around the intended center of the screen. Marius says shader tweak for macOS would be useful here. I thought about like hacking together a version of shader tweak that would work on the Mac. I think it would be really easy based on the code that already exists, but I haven't gotten around to actually doing that yet. But if anybody wants to pick up that mantle, I'd be a big fan of that. Cool. So we've achieved the zoom effect. This next one is kind of interesting. We want to do kind of almost a fisheye zoom distortion. And what that really means is that the distortion is proportional to the distance from the center of the figure. So we can kind of figure out what that means by working through it in code. So I'm going to keep this hack that actually does what we want as far as resetting to the center. And in essence, what I want to do is take that length again, I'll just call it L, the length of UV, right? And I want the zoom factor to be a function of that. So in this particular case, I'm going to use, actually, I'm just going to kind of get sloppy here and just multiply directly by it. I'm going to smooth step from a factor of 0 to a factor of 0.5 based on the length. Actually, since we want it to be less distorted towards the middle, I'll subtract 1 from L, since that's pretty much the maximum value that L attains. So let's take a look and see what that does. Whoa, not at all what we intended. Okay, so what went wrong here? I'm going to cheat real quick. I apologize. If anybody has ideas, by all means, feel free to shout them out. Oh, right. What am I thinking? Of course, like the length is I strike this this -1 here. I apologize for that. Right. So the actual intent was to smooth step right from 0 to 0.5 over over L. So basically, if you want to take a look at that, there's not a smooth step function in Grapher. I could I could probably hack one in a second, but in essence, smooth step is a function that allows you to smoothly transition from one value to another with a sort of configurable steepness to the step. So that third parameter there is basically the x value of this sort of S-curve. And then the corresponding y values are 0 to 0.5. So what that means is at the center of the image, right, we want essentially to be stepping very slowly through the texture coordinates, right? So that's why they look really, really big. And then towards the outside, we want to basically be kind of compressing them down. So that's why you get that sort of plumpness, is that basically the amount by which you're zooming is affected by the radius of the texture coordinates or the distance from the center, depending on how you want to think about that. Cool. Okay, so let's take a look at the next one. And we're not going to do all of these. We're just kind of going to, at this point, maybe see what suits our fancy and step through. I'm not feeling 100% today, so I'll probably limit this to no more than an hour, just in case anybody was getting itchy. So this won't, take too much longer. So the next one on deck is repetition. And we've already seen kind of what we need to do in order to achieve this effect, but for like one small bit. And that is, well, we don't actually have our sampler configured to repeat. So we need to kind of do whatever calculation a repeating sampler would do in order to kind of get this replication effect. And one thing that springs to mind immediately is we can borrow some of what we learned with Zoom to kind of make a step in that direction. And by that, what I mean is if we want to kind of minify the image, then we know that all we need to do is just multiply by a scale factor, right? And again, we want to multiply by a quantity that is larger than 1 in order to zoom. And again, remove these offsets because in this particular instance, we're kind of going to be tiling from the top left, so we don't actually need to correct for that. Okay, well, this is sort of what we want, and if the sampler were configured to wrap around instead of clamping to the edge of the image, then what we would be seeing is the correct thing here. But in fact, we don't. So like I said, we need to get a little bit more clever. And what we can do here is actually use a function called fmod. And the intention here is to basically wrap space. So what I'm going to do is say fmod of the coordinates by the let's just see what happens, because I confess I didn't go all the way through this one before. Right, okay, so now we're getting some repetition, and we want to probably, scale back down from that afterwards. Except not in that direction, of course. Right, cool, okay. So we've discovered a way to get 4 images, two repetitions in each dimension. And that suggests to us a general formula, which basically says, okay, well, if I want the reps to be equal to 2, then that's basically analogous to fmodding by this quantity 1 over the number of reps, and then multiplying by the number of reps. I did a quick little inversion trick there, but hopefully you're able to follow. Maybe to make this a little bit more apparent, I can hop back into Grapher and illustrate exactly what's going on here. So basically the idea is the thing that's analogous to fmod in Grapher or in common programming and math parlance is the modulus operator. So basically what that looks like is, let's say xmod 0.25. We can see that we kind of get this sawtooth pattern. And so basically what's happening is every time the value gets up to 0.25, it wraps around back to 0. And that's basically the effect we were after. We definitely want to repeat 4 times within the span of getting up to 1.0 in each of the axes. However, you'll notice that the maximal value here is actually 0.25. It's the value whatever you of whatever you're dividing by, in essence. And so we actually want to multiply by, of course, again, the inverse of that in order to actually get up to that desired maximal value of 1.0. So you can kind of see here now we're going from 0 to 1, 0 to 1, 0 to 1, 0 to 1. And that is actually what causes us to essentially, repeat the texture over the domain of the viewport. Hopefully that's pretty clear. And again, I think, yep. Well, we didn't actually get to the point where we had 4 of them on the screen. So just in the interest of looking like what the exam does, let's do that. Okay, cool. So that's more like it. Great. Yeah, so far so good. Now I could go on to implement the spiral and ray effects, but those aren't necessarily the most interesting ones, in my opinion. Spiral is actually just a combination of the zoom, distortion, and rotation. In essence, the amount that you offset the angle is dependent on how far you are from the center of the figure, in exactly the same way that the distortion was, the zoom factor was affected by the distance from the center in the zoom distortion example. If we have time, maybe we'll circle back to that. Anyway, let's go on to page 2 because there's some interesting stuff happening here. So the first one we'll take a look at is clamp. And the interesting thing to note here is that we're actually, of course, not clamping at values of 0 or 1. We're actually clamping twice along the y-axis, once around what looks like maybe 0.1 or maybe 0.15, and again down around the cheeks at somewhere around 0.3 or so. So what we're going to need to do is basically come up with a function that instead of mapping 0 to 1 to 0 to 1 as a line does, in essence we're going to have a couple of feet on our graph, so that we start out at a constant around 0.1 and then gradually increase up to 0.3 and then stay at 0.3, kind of clamping at 0.3. So there's a trick that I like to use that really comes in handy when doing stuff like this. And basically the way it works is you can use the min and the max functions to essentially write out code that represents the extreme edges of one of these, not step functions, but one of these clamped functions. So the way you write that is by taking the, I might get this backwards, but taking the max of the min of the first value, let's say 0.1, and then, it's actually not right, I did get it backwards. So it's the min of the max of the lower value that you care about, and the value under consideration, and the maximal value. So you can see that what we've done here is just ignoring the min and max part. This 0.1 represents the lower bound, and this 0.33 represents the upper bound. So we're kind of, again, sort of bending that linear function into a piecewise linear function. And if we go ahead and run that, yeah, that's pretty much the intent, right? I think I got the numbers closer this time than when I was practicing. I think that first value might be a little bit lower. But yeah, that's the basic idea, right? Let me know if I need to revisit any of these things, by the way. Still more than happy to answer questions. But if not, then we're just going to keep kind of trucking along. I expect we'll probably do maybe 1 or 2 more of these. And then, if I'm feeling generous, maybe I'll take some suggestions from the audience. So I really like this pixelize effect, and I think it's great for teaching a particular function that I'm very fond of, namely the floor function. So let's consider for a moment what we would want to do if we were trying to implement this pixelize function. What we want to do basically is scale the figure down so that it's kind of all crunched into space, and then kind of invert that operation while kind of still leaving that crunchy quantization in place. So it's kind of like in Photoshop, right? If you did a down sample and then you did a nearest neighbor up sample. Again, quantization is the name of the game here. So basically what we want to do, how we want to achieve that, is by constructing a function that instead of going from 0 to 1 in a line smoothly, we actually kind of want this broken step function that kind of samples from the same texel as we move across the image, basically sampling more coarsely than we would normally want to. And so the way we want to do that is actually, just get rid of that. And we're doing this in both dimensions this time. So we'll write a function of a two-dimensional vector. And so the idea there is that we want to floor the coordinates multiplied by some constant. I'm actually just going to pick an arbitrary constant here, and then we'll derive a better way to actually do this more flexibly. So I take the floor of uv multiplied by 30, and that those are all going to they're all going to take on integer values, and then divide back by 30 to get back to a normalized space that still has those steps in it. So you can see what I've done here is it's a pretty good result. The pixels aren't exactly square, and once again that's because of our aspect ratio. So we can correct for that by, instead of multiplying and dividing by the same constant in both dimensions, Instead, we can come up with separate constants for each dimension. And the way we can do that is thinking for a moment about what that number 30 kind of means. Well, what it means is that there are going to be basically 30 repetitions of this grid across the image. We basically crunched it down into 30 subdivisions. So what we can do instead is think about it in terms of how many pixels, what ratio do we want between pixels and texels. So what I want to do is write out the size of the image, again by using texture get width and texture get height. And then I might want to say, well, how big do I want each of these to be? So I'll just say the scale factor will be the size of the screen divided by, say, 32, a ratio of 32 between pixels and texels, right? So now we can multiply UV by the scale. The scale now is a two-dimensional quantity, again, that compensates for the aspect ratio. And ta-da, now we get even better results. We have square pixels again, which is what we wanted. Now you can, of course, plug in any arbitrary value here. If you go extremely high, then things get truly crunchy indeed. But you can also go in the opposite direction where, maybe it's a ratio of 4:1 and things are substantially smoother, but you can still definitely see that stair-step phenomenon. You get kind of this sort of low res sort of effect. So that can be useful if you want to achieve certain retro effects. It's a pretty cheap trick to do that. All right. So that is quantization and pixelization. Let's see what else. I like vague, which is to say wave. That will involve another trig function, either sine or cosine, depending on which one we want. Stepping back for a moment, Jeff asks, could one compress the vertex coordinates to the point that it pixelates? Interesting that you asked that. Let's think about what that really means, right? Like quantizing vector or vertex positions is sort of kind of like voxelization, right? Like if you snap vertex positions in space, then what you get is kind of, well, I don't know. Let's go take a look. Something like this glitch voxel phenomenon, or yeah, I guess that's the only one. It's kind of like this, right? If you essentially snap to a particular grid, then that's the analogous operation. I don't quite know how you would manipulate the vertex coordinates such that you got quantization in the texture, if that makes sense, because you're still by default going to get smooth interpolation over whatever surfaces make it through clipping and into rasterization. So, but it's an interesting question because there is in fact a three-dimensional analog, and that is to snap those vertex positions onto a 3D grid as opposed to snapping to a two-dimensional grid. Cool. Great question though. Okay, so let's step back and work on doing this sort of wavy thing. And what we can see is that what's happening here is that the x coordinate is being offset as a function of how far along the y-axis we are. So it's a function of y, but it produces a value of x, and it looks like we're maybe offsetting by up to maybe 25%, probably less than that, probably around 10% off that vertical axis. So that'll be a scale factor that we need to apply to whatever trig function we put the y coordinate into, and we'll just have to choose some appropriate scale factor for the y coordinate itself to figure out how fast we want that function to oscillate. So this is, kind of one of those situations where the artistry kind of has to take hold. We can set up the scaffolding for it, but we're never quite sure exactly what this is going to look like until we actually just see it in action. So what I'm going to do here is basically just start out by saying uv.x equals something, right? And I'm actually going to add it as an offset. So, I don't have to have a uv.x on the right-hand side of this expression. So I think what I want to do is let's just initially shift everything by 0.1. and see what happens. So we get a leftward shift because, again, we're kind of manipulating the space rather than the object. So that's useful. We could also go 0.1 in the opposite direction. Of course, that would be a rightward shift. But if we multiply that by, let's just say sine of uv dot y, and we need some factor here because that varies so slowly over the course of the image, right? It only goes from 0 to 1. So let's just say that we want, I don't know, like, let's just multiply by 60 and see what happens. So yeah, that's interesting. So now we're going to get an offset between minus 0.1 and 0.1. Oh, there it is. Cool. That looks about right. We could also crank up the factor inside the parentheses to get a faster oscillation, and we could manipulate this leading factor in order to, say, cut down on like how fast we're changing. If I cut it in half, then I oscillate less, right? And I could actually make this even more subtle, right? Like it's gonna be hardly visible at all, right? Just sort of a little blobby. Okay, so cool. That is vague, aka wave. All right. At this point, I think I kind of want to ask what you guys want to see. We've been at this for about 45 minutes. I'm, like I said, not going to do any of the ones that involve vertex shaders. I mean, I might actually show you how to do a wave as applied to vertex positions. I don't know if that's especially interesting. We could also implement like Lambertian shading, or if we were really, really ambitious, we could do toon shading. That's just, by the way, basically diffuse lighting plus one of those quantizing step functions. Okay, Michael says the shading one looks great. Screw it, let's just do it. Okay, so I'm not actually going to walk through all of the math as far as diffuse lighting is concerned, just because it's, you know, conceptually there are a lot of things that we would need to talk about. So and obviously also I can't do that in a fragment shader unless I have enough information there to do that. So instead what I need to do is actually alter the shaders from that produce that initial pass, the off-screen pass. So those are actually over in this other file. And it's actually quite straightforward. So, and we even already have the iNormal being passed through, so we can probably hack lighting pretty quickly. Yeah, Michael observes that the outline one, the cell shading one with the outline, is also interesting. It is. I definitely hope to get around to that. I know you already know this, Michael, but something interesting, essentially what you want to do in that case is look for fragments where the normal in eye space and camera space is essentially pointing to the left, or pointing sort of in a plane that's parallel to the near plane, right? So sort of as the facing of facets sort of crosses over that threshold of being pointing toward the camera versus pointing away from, that's kind of what creates that effect. There are some subtleties to it, but and especially so because if you want to achieve that effect, like, you're only rasterizing as many pixels as are actually in the geometry, so you kind of have to cheat a little bit in each direction so that you're actually hitting enough pixels on the outline of the object that the outline shows up, right? And there are other ways to achieve that same effect, but that's how I would do it as a first swing. Anyway, let's step back and talk a little bit about lighting. So what we're trying to do here is just come up with a simple function that makes our model look a little bit more 3D. Well, first of all, what I'm going to do is actually remove any coloration and instead just go all like solid white. So the way I'll do that is just say float 4. Yes, Michael's point is that making a nice and uniform outline is part of the challenge, and I completely agree. If I had more time today or I had done more prep, I would show you how to do it. Okay, So what I've done now is just replace that texture sample with a regular old solid white color. So let's see here. What I want to do is, yeah, we're just going to leave it untextured for the moment, and instead sort of work through some of the theory around inversion shading. So my scale factors are going to be totally messed up here. This is not at all designed to be physically based. Instead, what we're going for is sort of just, it's really just hackery. So what we want to do here is that the foundational thing is there's this central component in diffuse shading of in.L, right? In.L is the dot product between the surface normal and the direction to the light. And so when those things are aligned, we get a very strong reflection. And when they're at right angles to one another, we get no reflection. So that's what sort of creates that fall off that you see that's characteristic of that diffuse lighting. And so what we need to do is basically compute, first and foremost, the direction from the figure to the light. And there are at least two ways to do that, even within this common sort of blend-fong simplified shading world. I could represent the position of the light in camera space, and that would basically, I would then compute the difference between the point that I'm currently shading and the light, and that would give me the direction. Or I can just fake it with a directional light that's pointing in the appropriate way, and that will kind of have the same effect, but it will be more like a directional light, kind of like the sun, as opposed to a point light, like, you know, a light in a sconce or whatever. So what I'll do here is actually just define a pair of float3 values. What I'm going to do is extract the view space normal from the interpolated fragment parameters that I'm getting. So I'll say in float3 in equals in.I normal. Now that's not, I'm going to extract the XYZ, just swizzle those out because I don't really need that extra 0 on the end. And then I'm going to actually normalize it because over the course of rasterization, the normal can become not unit length. So it is pretty crucial for all of these quantities to be normalized in order for the math to work. And then we need the L, so that'll be another 3 vector. And in this case, I'm actually just going to say, all right, I'm imagining myself as the camera, right? I'm looking down the negative Z axis. So I want the direction to the light from the surface to be something, I don't know, I'm just going to eyeball it. Something like, I don't know, 001 roughly. Maybe there's an additional negative Y component that kind of sort of makes it so that it's darker at the top than the bottom. So maybe let's just go with that. So we'll say normalize float3 of no offset in the X because it looks pretty symmetrical. In the Y, we'll say like maybe negative 0.1. And then in the Z, a prevailing direction of 1. And that'll get normalized down to something that's not those values. That's probably a lot messier that I don't really care about. And then we just need to figure out like, well, what's the intensity implied by this? And again, like when N and L are aligned, in other words, when the normal, for example, is pointing back toward the camera, and since the light basically points in largely the opposite direction, those vertices on the front of the model that are pointing mostly toward us should get the most light. And then the way we compute that is literally nothing but say taking the I'm going to give it a highfalutin name, diffuse intensity, which is not actually a correct term, but whatever. Dot NL. Right, so here's something interesting, right? If we just take the dot product between N and L, then if we have a normal that's on the back of the figure, then it's actually, this quantity will go negative. In fact, this quantity will go negative for any face or any point that's pointing away from the light. We don't actually want that, so we actually want to saturate that quantity between 0 and 1, and that's exactly what the saturate function does. Now we're not actually using that yet, so what I am going to do is plug that into the color, Whereas previously we were solid white. Now instead we're going to be something else. Hey, actually that's not half bad, right? So I could go on to like manipulate the light direction further. It looks like maybe I underestimated the Y component. But the point is that, yeah, with comparatively little effort, right, you can get a not entirely terrible looking effect. Now, if I wanted to make this material look a little bit less papery, a little bit less diffuse, I could also incorporate a specular term. But you can see where this, where we might go from here, and that really was the intent. And just because we have a little bit of time, I want to wrap this up in about 5 minutes. But just because we have a little bit of time, I want to actually implement some like really cheap toon shading, and that's again going to just bring back some of this quantization and thresholding that we were doing earlier. So what I'll do here is basically say, okay, I know that I have actually I want a little bit more of a stark contrast. So I'm going to move that light down, maybe to like 0.4 even. Yeah, so that gives us a little bit more contrast on his head here. And so now what I can do is actually, instead of just using the diffuse intensity directly, I can manipulate that. And the idea here is that we're going to, you know what, that is getting really tedious to type, and I'm a slow typer, so I'm going to make this easier on myself. All right, so basically what we want to do is multiply again by a factor, in this case the number of steps, and then take the floor and then divide back by that number of steps. So I'll go ahead and define a steps value here. We'll just start out with 4. Fewer steps, of course, will introduce more banding. More steps will make it a little bit smoother. So if I multiply by steps and then divide by steps and take the floor in between, now I should get something that is more quantized in the grayscale. There we go. Cool. So that's really rudimentary toon shading. And by the way, if you want to, you can actually bring back in the texture by multiplying by the intensity that we've created and the value at the initial UV coordinates. So let's bring that. It's actually, it's already right there. Okay, cool. So this will be like our kind of base color. And if you multiply that by, right, not exactly. Right, multiply it by that diffuse intensity, what we get is essentially that texture modulated with the lighting. And so now we get this sort of dramatic cell shaded Pikachu. It doesn't, of course, look terrific, but again, this is just sort of like, it's all cheap hacks, right? Learning is the essence. So with that, what I'd like to do is take just a couple of minutes and see if there are any questions that have arisen, or if there's anything that we'd like to like revisit or go back to. I'm more than happy to keep working through this stuff. Anything that hasn't already sort of been elucidated in your minds. But if nobody says anything in the next minute or so, then we'll just call it done. Greg asks, what's your favorite Pokemon? It's been so long since I've played a Pokemon game. Probably Eevee, if I'm being honest. Jeff also asked, on the rotation exercise, if we did that rotation in the vertex shader, would we have to worry about the aspect ratio? No, and the reason for that is the axes in 3-space, in that space prior to clip space and prior to texture coordinates and normalized coordinates and so on, those axes are all of the same length. So there's no real notion of aspect ratio until you kind of cross, I don't want to misuse the phrase cross the Rubicon, so I'm not going to say that, until you actually cross over into texture coordinates. In other words, like if there's a transformation that's going to apply that non-uniform scale, then you definitely do need to compensate for it. I could mention, Michael is insistent that I could mention that visualizing texture coordinates as colors often help. True. So with the last minute that we have here, I'll just go ahead and show you how to actually do that. So in this instance, I'm going to strike out the diffuse stuff just so it's a little bit more obvious what's going on, and just go directly from the base color, except that I don't want to use the base color. What I want to use is the, let's say uv.x, uv.y, and 1. So that'll be like a solid blue. Do I have UVs? I don't have UVs. So let's make those again real fast. Float to right. And we have 3 elements, but of course we want, you know what, we're just going to be really cheesy right now. Okay. So yeah, it can be very helpful to visualize texture coordinates in, this is actually not looking terrific. I'm going to make that blue 0 instead. It's not especially helpful in this particular context because the map of this model is not at all smooth. It's actually pretty chopped up. So I can just open the PNG, and it's like, yeah, it's not nicely unwrapped. But if you were generating texture coordinates, or you know, I often find that it's really useful to visualize iSpace normals by doing this kind of same trick where you just emit, instead of emitting a sampled color, you emit some quantity that represents you know, something that's varying over the surface for the purposes of a sanity check. If you guys saw my video of ARKit content rendered in metal a few weeks ago with the sphere kind of stuck to my face, like those were iSpace normals that I was visualizing for debugging purposes. Yeah, okay. Well, I guess we're about done. This has been a lot of fun. Thanks so much for tuning in. I hope to do this again. If not next week, then on a pretty regular basis. Michael says again, I meant the in texture space of the 2D plane to show the distortion. Yeah, that's a good point. Okay, so apologies. I may open with that next time, but essentially the idea there would be that instead of visualizing the UV coordinates on the model, once you were back in the post-processing shader, that full screen quad, you would get a better visualization of how texture coordinate spaces are being manipulated by those various offsets and multipliers. Good note. I should have done that up front. And yeah, I find that, like, however many tools you have for visualizing this stuff and making it a little bit more intuitive, yeah, the better off you are for sure with each one of those. Okay, I guess we're done. Thanks again for tuning in, and chat with you guys later.